So in the final chapter of our EC 301 workbook, which is 8, which is at top of page 95, we consider what are called first order RC circuits. So this case, we're looking at using both loads or resistances and capacitance in the same circuit. There's also what are called RL circuits, where you have resistances or loads with inductors. And you can actually have what are called RLC circuits, which you have all three types. But we're going to finish out the course by just looking at this particular scenario and see how voltage and current change when you have both of these types in the same circuit. All right, so in the circuit below, the switch is going to be closing at time t0. And so as indicated here, we have our capacitance with a voltage V sub C across it and the resistance R. Now, when the switch closes at time, let's say t0 equals 0, so after time 0, we have these two items in parallel. These two elements are in parallel, so that the voltage across this capacitance will be the same voltage across the resistance, right? And we're going to assume that that capacitance is charged to an initial voltage V sub I prior to closing the switch. So if we were to write a current equation, or basically think of KCL, the top node, after that switch has been closed, then we can see the current flow. Let's assume that we're coming down through the resistance, and that will make that PRC. But they will not be PRC when you come up through the capacitance, so it will discharge the energy. And so you would end up, if you were writing equations for current, you would end up actually with the incoming current here would be represented as a negative, and then the outgoing would be a positive. But if you added the two together, this is what you would have. So this is our representation of current for capacitance. This is the representation of current for resistances. And of course, you pull one of the terms off to the other side, you can see they're going to be opposite in sign. And that is going to make sense because, again, the current's going to flow one direction through around. You want to think like a mesh current around line. So in this case, it's definitely not going to be PRC here, but it would be PRC there. So a little bit of algebra now, just to manipulate this equation right here, which involves derivatives. And you could see that you could multiply through by the resistance and get RC times the rate of change of the velocity of the voltage through the capacitance plus that same function equals 0. And if you recall from differential equations class, this is a first order linear differential equation. And the solution to this type of equation, in other words, looking for voltage functions so that a constant times its derivative plus its derivative could give you 0, means the function's going to have to be exponential. Because to be additive, the only kinds of functions whose derivatives pretty much take the same form or shape as the original function are exponential functions, right? So in this case, we can assume that that voltage function has an exponential behavior like this, of the form, say, k e to the st, where k and s are constants. So if we assume that that is the correct form, which seems reasonable for a solution to this first order differential equation, then we would get the following result here. In other words, we would plug in k times e to the st here, take its derivative, add it there. This is going to be the derivative term, because you'll get ks, the constants, times e to the st. The RC constant still there. And then what you can see, factoring out the KEST term, you would have this, all right? So if we solved this homogeneous equation, in other words, if we set this equal to 0, okay, which is, again, what happens here, all right, we're setting it to 0, then we would be able to show, well, the exponential term is never going to be 0. No exponential function can ever be 0. It's asymptotic. So the only way you're going to get 0 is that the S value would have to be -1 over RC. The -1 over the reciprocal of your resistance times your capacitance. So in that case, then we've solved for S, and the voltage across the capacitor has this kind of form, all right? It's some constant times e to the -t over RC power, okay? And of course, we would have to use some maybe initial condition to figure out for a specific problem what that K constant is. So since current is finite and the voltage across the capacitor cannot change instantaneously when the switch closes, right? So we will define, say, the initial voltage this way, so that just right after the switch closes, that's what the 0 plus is indicating there, that voltage is this initial amount, V sub I. Okay, it represents the time, again, 0 plus, immediately after the switch closes, right? And so if we do have VI voltage there, then what we would do is set this function VC of t right after time 0. We would set that equal to the initial voltage, plug in time 0 here at the top, all right? And if we do that, then we'd have k times e to the 0. So that tells us exactly what that constant will always be then. So that constant will be the initial charge, excuse me, the initial voltage on your capacitance. So this is a description of how the voltage across the capacitance is going to change. It initially has that value of VI, but you can see now as time marches forward, RC is a constant, that's a positive constant. You're going to have negative T over this positive integer there, whatever it is. And so through time, that's going to degrade exponentially to 0, and you're going to run out of voltage altogether. In other words, you're discharging the capacitance completely, all right? So we'll draw a little figure here to sort of illustrate this effect, all right? And so we're going to draw just a very simple curve here of voltage, all right? So the y-axis, excuse me, the x-axis, or in this case, the t-axis will be horizontal, and we'll just represent that by, here's our time axis t, and then we're going to draw a voltage y-axis here, and we'll draw it something like this. And what we're interested in showing is how the voltage across the capacitance changes. And of course, the units are volts. So couple of interesting things to note. Again, our function is of this form. Vc of t is Vi times e to the minus t over Rc, okay? So a couple of things that are interesting to note are specific values, all right, which we can immediately get a result or fraction of the initial velocity. One thing is to notice, what if we were to plug in, for example, the particular constant R times C, and we actually will give that a name, a Greek letter called tau. And specifically, what tau is known as a time constant. And all it is in our case is the product of your resistance times your capacitance. And if you were to plug this RC value into the function there, what would you get? Well, you would have your initial voltage there times e to the, that's right, minus RC over RC. So what you'd really have is just VI times e to the minus 1 power, or what you would have is just 1 over e times VI, which is your initial voltage. So at this particular point in time, this is the fraction of the initial voltage that you would have. If you took a calculator out, that's exactly 0.368 times your initial voltage, about 4/10, just less than 4/10 of your initial voltage. If you kept looking at multiples of RC, for example, so another way of saying that is VC of tau is equal to 0.368 VI. If you were to plug in 2 tau, in other words, twice the RC value, right? Well, then you would end up with 1 over e squared times the initial voltage. And that's just going to be 0.135 times the initial voltage, okay? So time constants are a very common way of describing the degradation in your voltage through time, right? For capacitance that are wired up with resistances, loads that are going to absorb the energy, okay? So what we can do then is write, let's suppose this is a representation of the initial voltage that's on your capacitance. And then if we were going to draw, say, 2 time constants, one of them would be, well, whatever that value is there, times 0.135 VI, that's the second time constant. The first one would be a little bit above it, and that would be, say right here, 0.368 times the initial voltage, okay? And so maybe we'll just kind of hash out, just so for drawing purposes, those levels. So we'll have levels representing the time constants. And again, you can keep doing that with 3. As you get higher here, you're getting closer to 0. Again, this was 1 time constant at 0.368 VI. This is the second one, the third one, the fourth one. They're all getting very close to 0 because exponentially you're going to 0. So what's happening here is if this represents 1 time constant, and let's say this represents 2 time constants, 2 tau, then we know 2 points immediately. We know that this is a point on the curve, and we know this is a point on the curve, okay? Again, because these are the representations that we've already determined from just plugging in specific values of time. And then what we would do then is draw the curve looking something like this. And what's happening, of course, is it's eventually getting closer and closer to zero, right? Okay. So this is an illustration of the discharging. Certainly, you're going to be discharging energy from the capacitors for the load to absorb, okay? And this is kind of representing how that drop occurs. Slope the slope starts flattening out as you get through so many time constants. And in general, what people are interested in is how many time constants are you essentially discharged? There really isn't hardly anything left, okay? All right, much like your garage door opener, once you close the switch, you can imagine the garage door eventually comes down and shuts, then eventually you need all the power to be dissipated totally, okay? All right, so if we flip over to page 96, a couple of other details, just indicating in words what I just mentioned. That tau value is called the time constant. That is R times C. And some people would say, of course, it's the amount of time it takes your voltage to decay, because it is dropping. And because it's dropping exponentially, and exponential decay functions typically are written as that, or just called decay functions are usually represented by exponential functions. Sometimes they use that word decay. And we know the reciprocal of E is 0.368. Generally speaking, what people observe is after about 5 time constants, 5 times RC, you pretty much you have very, very limited voltage, practically zero, okay? So you use these kinds of RC circuits in timing applications, okay? The garage door opener is what I said here. You might desire that light is on for a while, and then how long should it stay on depends on how much power you're going to generate to it. And this will be a good illustration of designing it so that after so many time constants, your light goes out, right? So let's look at the next case. Oh, and by the way, the resistor would be needed because you need to, if you're going to discharge the capacitor, you have to have resistances to absorb the energy, right? So that's important, okay? A sensing circuit could keep the light on as long as the capacitor voltage is larger than the value that's available, but you want those resistors to absorb that energy and discharge out that capacitance. Now, in the presence of a source, though, that was illustrated without a source. Now, if we look at section 8.1 or on page 96, now suppose you have a voltage source here, and this is an independent voltage source, and we're going to specifically assume it's a DC source, so that the current is constant, okay? All right, so here the voltage is constant, or I said that, so the voltage is constant with this DC source, and we'll assume the initial voltage across the capacitor just before the switch closes. If you're talking about right before the switch closes, we use sometimes this notation: 0 minus, just instantaneously before you close it. 0 plus would be just instantaneously after you close it. So what we want to do now is solve for the voltage across the capacitor now, where let's say you have nothing, there is no voltage on the plate. You close the switch, start delivering, so in other words, you start discharging the energy from the voltage source. It's absorbed by the resistance, and you're going to absorb it by the capacitance. These two are in series, okay? All right, so first, we're going to do this on the next page in the top box on 97. So this is our design, a very simple design, DC source, close the switch, resistance, capacitance. So we start by just defining the current equation that we would have. And again, using what we know about the representations of current, well, we would have for that capacitance, we would have the capacitance constant, C times the rate of change of the voltage through that capacitance times dt, all right? And so, and the way we've written it there, we would have it in PRC because we're going to absorb the energy, and so we won't put a minus sign there. And then we would need to represent the current flowing between the to remember, you have voltage available on both of those sources, I mean, between the capacitance and the voltage DC source. So we could use our NVA approach, our node voltage analysis, to say, well, the representative of the current in this case would be V of C of T minus the voltage source divided by the resistance, okay? And that would be equal to 0, okay? All right. So again, maybe just to illustrate why that is, if we go back and draw the circuit, just so ever briefly here, so we can make sure we understand what's happening. We close the switch, we have the resistance R, and we have our capacitance here. Here's the voltage representation, VC of T, the polarity there, and there we are. So we're going to assume the voltage here is plus minus going to the resistance. So we're going to assume we absorb the energy, and then we come in here to the capacitance here. So we are looking at the representation of current representation at this, let's say, flowing through the top node here between the voltage and the resistance. And so we know that we have this voltage over here, the voltage over here, VC, and the way we're representing it here is we're representing it going left to right, okay, through the resistance, whereas the current flowing representation through the capacitance is represented here this way. So a couple of things on that. If you want to think about the fact that you have the node that joins, excuse me, I said that wrong. I got the wrong pointer there. We're looking at a current equation for this node. So let's sketch it in. That will make more sense. So in this case, we're representing outgoing and incoming. And so if we were representing incoming this way, then we would represent the current flowing from VC to VS through R. And if we're coming the other way, we're representing it in this direction, which would represent being PRC coming into the capacitance this way. So either we're representing it going back out this way, or we're coming down into it. And if we're coming down into it, we're going to represent that as PRC. Otherwise, we're going this direction. We have voltage here, we have voltage there. Now, there may be zero voltage there, but we're representing nodal voltages. We're going to represent this voltage and that voltage, so we subtract that. So outcome going equals incoming there, all right? Or in this case, the sum of the two will be equal to 0, all right? So, so now what we're going to do is simplify this equation. And if we're simplifying this equation, then what we're going to look at is multiplying through by R again. And now we have this representation, RC times the derivative of this voltage across the capacitance plus the voltage capacitance. Now, the difference between the previous equation is that's not 0. So that's really the only difference that we had before. If you go back, just for example, to turn back to see what we had in the previous section, I just want to review this. Remember, we had this representation before. There was no voltage source here. So RC times the derivative of VC of T plus VC of T equals 0. That was on page 95. Now we're on page 97, and the only difference is this term. See, that's the only difference, okay, is that we now have a voltage source there, right? So the voltage across the capacitance cannot change instantaneously because voltages are finite and the current through the resistance finite. So we're going to make some initial assessments here that the voltage, again, after the switch is closing and right before the switch is closing through the capacitance is 0. So there's no energy available to dissipate in this particular scenario, okay? The capacitance can't offer anything up to the circuit, but it's going to absorb the energy that the voltage source is going to provide, all right? So in this time, we're trying to solve an equation of this form, all right? So we could argue, well, can't you just use the same form of the solution last time, a constant times e to the st, all right? So if you remember, if you've had differential equations, this is using a technique called the method of undetermined coefficients. I'll just write that down. I'll just explain what the ultimate result of it is. You don't really need to go and look it up if you're not familiar with it. But basically, it's pattern matching that we need to be able to find a solution. We need to be able to determine a solution. We need to determine a solution that basically will be able to plug into the left-hand side, but we must produce a non-zero value, okay, on the right, all right? So to do that, we need to use more than K2, a constant times the VST. We're gonna match up another form to the right-hand side as a constant itself. So what we're saying is that the solution to the differential equation is gonna also have to have a form with a constant term in it, all right? You'll see why in just a second, all right? So if we substitute this time, so we're gonna try this as our solution. We're gonna use two constants, not just one. 2K, so to speak, okay? The reason why is because I need to match up to a specific voltage source here when we plug in 0, okay? So if we do that, then what we would get is plugging it into the differential equation up there, what we're gonna get is basically 1 plus RC S quantity times K2 e to the ST plus K1 has to be equal to Vs, okay? That's just what's gonna happen when you plug that in. Again, you have a DC source providing this voltage, and if you take the derivative of this term, right, the derivative of the constant is 0, the derivative of this term is gonna be K2S, right, times e to the ST, and that's why you have an S term sitting here now, all right? But if for a DC source, remember we set this equal to 0, all right? So we must have, let's just say it this way, we must have 1 plus RCS equal to 0 so that we could possibly match the left side to the right side now. So look what we have. We have an exponential form over here plus some constant, and we're saying it needs to be equal to a constant. Well, how can that possibly be mathematically? The only way that could happen is that the 1 plus RCS scalar is actually equal to 0. So we need to have that to happen, which really says that what S has to be for this case is -1 over RC. And that will tell us initially that, well, then that means that K1 basically has to be Vs. Because if I have S equals to -1 of RC, right, that wipes this term out. So then K1 would have to be equal to Vs, right? Another thing we know that Vc of 0 plus right after the switch closes is 0. And that's going to be what? Vs plus K2 times e to the 0 power. Because I've already said that K1 is Vs, all right? And so I can substitute Vs here. When you plug in 0 there, that's just going to give you a K2 term. So that tells us that Vs, the voltage source, plus K2, the sum of the two must be equal to 0. Why am I setting it to 0? Because that was our initial condition. This is our initial condition that we assumed is true, that there is no voltage on the capacitance. So what that tells us then is that your K2 parameter here is just the negative of the voltage on the source. So finally, this is what your function looks like for your voltage on your capacitance when you have a voltage source supplying energy, right? But you have no initial voltage on your capacitance. So it means this is what you'd have. And you can algebraically clean this up a little bit. It's Vs times e to the minus t over RC power, okay? So that's a very nice form. It kind of tells you what's going to happen. Initially, when you plug in time 0, or right after it, so to speak, you've got the voltage source available to you, but then it will degrade again, okay? It'll just keep degrading and degrading and degrading, okay? All right, so that's what we've derived down here. all right? And then we can look at it from the perspective of time constants. Again, the time constant is RC, and maybe we'll draw this curve to get a realization of what happens to the voltage now, at least after two time constants. So we're looking at the difference between this function, Vc of t, Vs times 1 minus e to the minus t over Rc, versus the function we had just a minute ago, correct? Which was V of c of t is equal to initial voltage on the capacitance times the quantity e to the minus t. Very subtle differences here. They look very similar, don't they? But they're actually very different, okay? Again, this is from a DC source. This was initially on the capacitance or the capacitor. You had it already charged. So what does the voltage curves look like when you have a charge? We've already seen that one down here. What does it look like when you don't have a charge, but you have a DC source applying the voltage to you, all right? So we'll draw our axis here. Again, there's our time axis here at the bottom. Remember, time constant is RC, so we'll mark one time constant. We'll mark two time constants. We're drawing that same Vc of t idea, but for the voltage here. But this curve looks different, okay? So what we've got here is we've got to be careful here, because let's look and see what this function is going to look like with time constants. So we're interested in this representation of voltage now. So when you plug in one time constant, like RC, you're going to get Vs 1 minus e to the what? Minus 1 power. So the scaling factor is a little bit different. It's 1 minus 1 over e times the voltage of the DC source. And I've already computed that for you. 1 minus 1 over e is the same thing as 0.632 Vs, okay? So 1 minus those reciprocals is a little bit different value, okay? And the same thing when you plug in the second time constant, I'm just going to say 2 tau here, you're going to get Vs times 1 minus e to the what? Minus 2 power, right? And that value, which you're going to get out of that, is 0.865. Notice it's increasing now, times Vs, okay? Going a different direction than we saw with the time constants for this other function that had no voltage source, okay? So if we represent our initial DC source voltage here, whatever that value is, then one time constant is going to be a little over half that value. So put it down here, 0.632 Vs. And then the second time constant is really getting close to it, right? 0.865 Vs, okay? Very close to it. So we'll just kind of hash those lines across so we can draw our curve. And we know that at one time constant, I would have to be here. And at two time constants, I'd have to be up here. And so, and maybe just to illustrate, you can't have any more voltage than is available in the system, in this case from the independent voltage source. So there's your new asymptote. And so when you sketch the curve now, again, you have no voltage on that capacitance, 0. Close the switch, and then through time, notice what's happening. It's eventually going to get closer and closer to the voltage that is available, okay, from the Vs. Now, it won't get quite there, okay? It's going to be asymptotic. That should make sense because you do have a resistance, okay? So because of the resistance, I mean, if that R parameter wasn't there, then no, that wouldn't be the case, but you've got that resistance. So it's not gonna get at Vs, but it's gonna get it could get fairly close to it, depending upon what the values are, okay? So you can control how much you're going to get based on how much resistance you're going to put in, or how much load you're going to put on the system. But notice the intended effect. The intended effect now is to charge up that capacitance, right? And then you could unhook that DC source and then use that voltage that's stored in your capacitance, or switch it off again, right? And it's available to use somewhere else for some other component in the network, okay? So that gives us a good idea of what the use of that resistance could be and network resistances. Let's just turn over and finish this section to page 98, and then we'll end this particular lecture by realizing, of course, that after one time constant, the voltage has gotten to 63.2% of the final value. And again, you generally reach a steady state about after 5 time constants. So in summary, several time constants are generally needed to charge or discharge a capacitance. We've illustrated both. We just did the case of charging, we did discharge earlier. This cost and time is considered a limitation of the speed at which computers can process data. It's generally not possible to build circuits that do not have some capacitance that is charged or discharged when voltage is changing value. That's just a practical aspect there. And circuits always have non-zero resistances that limit the currents available for charging and discharging, okay? We need those loads, right, to absorb the energy to discharge. Some non-zero time constant is generally associated with each circuit in a computer, for example. So you have time constants that will basically be calibrated to the clock cycle of that particular circuit, okay? So we'll stop there and finish the last section and the next lecture, and we'll be talking a little bit more about this idea of steady state through time for DC sources.